All right, folks. So today is the 11th of February, 2021. Welcome to the future. The thought for the day comes to us from Iris Gonzalez, who you may remember from a recent visit. Be clear, be transparent, be prepared. Be prepared to show your sources and be prepared to show your methodologies that back up your analysis. Right? And that idea is rather than rolling in and saying, hey, everybody, I built something super fancy that gives a prediction, you got to be ready to explain how that thing works, right? And I think that ties into hypothesis testing because we need to be able to establish relationships with some rigor rather than just eyeballing if things are moving together, right, or if things are different than one another. On the announcement side of things, yeah, take care of your pets, your plants, and your pipes. And I don't think we have any other announcements coming up. I don't think we have a speaker this Thursday. This today. I could be wrong. So bring in your pandas, wrap up the bamboo, water the bamboo, and then wrap it up in a. Bring your pandas indoors. On the agenda side of things, folks, we're going to be doing two things today. At the very least, two things. I think this is the right amount for today. Let's see, today is Thursday, so lunch is at 12 to 1:30. Don't forget. All right. So we're going to introduce this concept of hypothesis testing and introduce some vocabulary here around this topic of hypothesis testing. And then we're going to introduce our first type of hypothesis test called a t-test. And that's where we're comparing the means of two different groups. And depending on what we're trying to measure, right? Generally, if we're looking at means, we're trying to compare something continuous, right? And so we want to compare a continuous value and the mean of that continuous value between two groups. And a t-test is the right tool for that job, okay? So I want to put a call out. Any questions, comments, or thoughts before we jump into the overview of hypothesis testing? It's kind of like a sub-module here. I want to give you all a chance to, if you have any burning questions right now. Otherwise, we'll just jump right into it. All right, let's jump into it. So we're in the stats module of the curriculum, and we're in this little kind of submenu called hypothesis testing. And hypothesis testing is a huge deal. Huge deal in statistics. It in fact is kind of what makes inferential statistics, the whole branch of stats that's concerned with coming to conclusions. And what we're going to be doing here is we're going to be comparing one hypothesis to another and using some of our statistics chops to help us with that. This first overview is going to be pretty high level, right? We're not going to get into any code in this overview, but then by the t-test lesson, we'll get into some code, okay? So in this module, folks, we're going to be working with three different types of tests, and I'm going to pull over a little diagram here. We're going to be working with t-tests that we covered today. We'll be working with correlation. That'll be tomorrow, and then chi-squared will probably be tomorrow. And what we're trying to do here, these three tests are for different types of data. The t-test is going to be for comparing a continuous measure among two groups specifically, whether if it's a subgroup versus the population or two subgroups compared to each other. When we talk about correlation, we'll be comparing two continuous values together, like sales and tax or sales and tip or something like that, right? Things we want to, rather than assuming things move together, we need to answer the question, how much do they move together with correlation? And should we even believe the fact that they move together? And then once we make it to chi-squared is where we're comparing two different categorical variables together. Okay. So that's a little bit of the preview of coming attractions. So let's see, we're going to hit some of our vocabulary terms, and the one that I want to make sure to really drive home is this concept of what I've talked about. We're going to compare hypotheses or evaluate the hypotheses. And with hypothesis testing, we're always going to have two different hypotheses. The first hypothesis is what we call the null hypothesis. And let's try and dig into this. I think the word null explains everything about this. So the null hypothesis is the guess, or it's the postulation. It is the hypothesis that there is no difference between two groups or between groups. So if we looked at different chunks of data, like if we looked at shoppers at HEB in the lunchtime versus shoppers at HEB in the evening time, the null hypothesis would be that they have exactly the same behavior, basically. So whatever thing we're looking at, the null hypothesis is always centered around, that's our default hypothesis, and it's always centered around that there's no change, or there's no effect, or there's no relationship, or if we're talking about correlation, there's no correlation. If we're talking about t-tests, the means of two groups are exactly the same, or just within rounding error of each other. We might ask questions like, are there more whatever our null hypothesis is, it's always that there's no change, there's no effect, or there's no difference. And it's kind of right there in the null word. There's null difference between groups. And what we're doing with hypothesis testing, folks, is we're trying to, we can't just accept any old hypothesis, but what we're trying to do, and what gives us some rigor here, is we set our environment up so that we either reject the null hypothesis or we fail to reject the null hypothesis. So rejecting the null hypothesis would be, well, we compare customers at HEB and lunchtime, and we compare customers at dinner time, and we notice that their average spending is very, very different, right? They're not the same. They're very, very different. So in that case, we would reject the null hypothesis. And when you reject the null hypothesis, this one's kind of tricky. We don't say that we accept the alternative hypothesis, but we say we have reason to believe that the alternative hypothesis is the case. And so this method of thinking takes a little bit of practice, just a little bit of practice. So let's say if we set up a scenario, let's set up a little scenario. We can say, could data science students drink more coffee than could web dev students, right? So I'm just making this stuff up, throwing it out here. Our null hypothesis is that there's no difference. So same consumption rates. And that's because we can disprove the same consumption rates. And that means that the alternative hypothesis is that the consumption rates are different. And depending on how we set up our test, we can set the test up to measure if the consumption rate is different, or if the consumption rate is higher or lower. But that null hypothesis is always and forever, there's no difference, right? Yeah. And for statistical rigor, we're not saying we accept the alternative hypothesis, but we do say we either reject the null or fail to reject the null hypothesis. So failing to reject the null is not the same thing as confirming the alternative hypothesis, but it is saying, given the data that we have, we are not able to disprove the null hypothesis right here. Okay. We're going to be introducing a whole bunch of italicized letters in this lesson. I think from this little chart here, there's two things that I want us to pay attention to, like statistical power and the false negative rate. Those are pretty damn important. Let's see, the significance level is something called alpha, and that is what alpha is. Alpha is our confidence, is 1 minus our confidence level. So what is our confidence level? So our alpha would be 1 minus, what is our threshold for accepting findings, even if they're random. So our alpha for something like, let's set our confidence level to be 95%. So what this means is that our alpha will be 1 minus 0.95, which is 0.05, which means that with this alpha, we're saying there might be a chance, in fact, there is a 5% chance that we will see the results that we see just due to randomness and comparing two means. So 5% alpha is not great, right? What if we were in manufacturing or something where we had higher tolerances? 0.99, our confidence level then becomes 0.01. So if our confidence level is 99%, then our alpha, our ability to say, well, there is a chance that we are seeing the results given some chance, but that's much lower. That's 1%, right? So here's the thing. You set your confidence level and your alpha before you run any experiment. If you get some experimental results, it may be very, very tempting, and it certainly is very tempting to some folks with funny ethics, maybe very tempting to assemble a story to explain the problem rather than saying, okay, how much are we going to be able to accept how much is randomness an explanatory factor in what we're doing? Okay. The beta is the false negative rate and the alpha is the false positive rate. And those are both really, really important measures. False positive rate, that's how many false alarms you have, right? The false negative rate, that's how many misses you have. So our false positives, that's called a type 1 error. A false negative is called a type 2 error. But here's a different way of looking at it. Boy Who Cried Wolf and hypothesis testing. So we all know the scenario. Boy cries wolf. Boy cries wolf. So that the boy who cried wolf is making a hypothesis. I mean, certainly more than a hypothesis. The villagers believe it. Right? They believe it, but it's not the case. So this is a false alarm, right? Boy Who Cried Wolf says there's a wolf. The villagers run out. They're ready to whoop some wolf butt. But it's a false alarm, and a false alarm is a type 1 error. False alarm. So this is like a type 1 error. This would be like your check engine light comes on, but everything is okay. False positive, right? False alarm, false positive. And this is a little trick. The boy who cried wolf is a trick to try to remember which types of error are which. The type 1 error comes first in the boy who cried wolf. The villagers believe the hypothesis, but it's not the case, so they have a false alarm. Now, boy cries wolf a second time. And yet again, the villagers roll out and make another false positive, another false alarm, which is type 1 error. And then the boy is like, "Oh man, I'm having a great time here." Boy cries wolf. But there is a wolf. The villagers are tired of the boy's stuff, the boy's shenanigans. Villagers disbelieve the hypothesis, and I think they have good reason to, right? They disbelieve the hypothesis, but the wolf was real and gobbles everybody up. So this is a false negative. And looking at a little bit more of another real world example of false negative, another way to say false negative is a miss. In plain English, a false negative is a miss. The prediction said that there wasn't something there, but there was. The prediction said there's no wolf, there totally was a wolf, and everybody got gobbled up. So consider that with a car example, check engine light stays off, but there's a problem. There's some sort of problem. So that's a miss, right? So this is type 2 error is the second part of the boy who cries wolf. Type 1 error is when the boy cries wolf and it's false. And if you tell the story back to yourself in your head or in an interview or something like that, the order of the different errors helps you realize, okay, which one is which, because it can be I mean, there's only two, the false positive and then a false negative. There's no other types of false, right? I guess there's true negatives, but that's a true negative. Yeah, let's build this out just a little bit more. True positive, that's check engine light goes off and there is a problem. So the check engine light worked. A true negative, the check engine light stays off. Man, I need to work on my language here. Goes off, stays off. We'll say turns on. There we go. The check engine light remains off, and everything is fine. That's a true negative, right? We predicted that something didn't show up. The reality is it's not there. We're good. And then we have a false positive, false alarm. And a false negative is a miss. So false positive is the engine light goes on, but everything's cool. A miss or a false negative would be engine light stays off, but there's actually a problem. And I'll be sending out these notes to you. I know I'm typing as I'm going here. So I think these four definitions of true positivity. So the true or the false is the reality, right? True or false is the reality. Positive or negative is the prediction. Are we predicting the presence of something, or are we predicting the absence? Okay. The concept of true negatives, true positives, false positives, and false negatives, this is going to come up again, not only in hypothesis testing, but when we are working with classification. algorithms in machine learning, we will get back predictions, and predictions are either positive or negative, just like a positive or negative on like a flu test, right? Or positive or negative on any other kind of like medical test, right? And then the true or false is the reality of the situation. So we can have true predictions that nothing happens, false alarms that something exists, and then misses. Okay. Oops. So I like to any kind of alpha or beta, forget about it. Forget about it. Think about it as a check engine light. The positive prediction is that the check engine light goes on. Whether it's if it's true or not, true or false, that's whether if there's actually a problem. Okay. All right. I want to open up for questions right now if you'll have questions about what I've covered so far with this concept of positive versus negative. I mean, we see that in all kinds of stuff, but think about it as a check engine light is my encouragement. If you ever need to just play back The Boy Who Cried Wolf in your head, type 1 error is the first error that the villagers make. And they make it once, twice, right? And then type 2, and it's a false alarm. They're freaked out. They're running. They're grabbing their pitchforks and torches and everything. Everything's cool. False alarm. Type 1. Type 2 error. Boy, there actually is a wolf, and the boy cries wolf. But because he didn't have any more professional credibility with the neighborhood, they succumbed to the type 2 error, which was, we don't believe that. So that's a miss. That's a miss. Okay. I'm sure I'll be adding to these, but I think the false alarms and check engine lights, I think that's a little bit more applicable than alpha and beta. But when we look at, remember I said alpha and beta are rates, they're percentages, right? And so if we have a lower alpha means lower tolerance for getting the results we get from chance or randomness. So if you crank your alpha way low, like 0.01, or if you're really feeling spicy, right, you could do 0.999, and then we'd have 2 zeros and then a 1. So we're accepting less randomness as an explanatory, or in interpreting our results, we're saying, okay, mathematically, if we accept a result with an alpha of 0.001, then there is a 0.001% or 1% of 1% chance that what we're seeing is due to randomness. So have y'all ever seen like in studies, maybe in magazines or something like that, where they list the confidence, they list the alpha next to something, next to the findings, maybe medical stuff. Yeah, a lot of social science, like sociology papers and stuff like that, are much more comfortable. I'm not doing a dig on the social sciences, but like economics as well are much more comfortable with higher alphas, rather than if we were doing manufacturing or if we were doing something like designing, I don't know, heart stents or something. We would want to not have a very high alpha there.
I was actually just reading a paper last night, and because I was watching a video on hypothesis testing, and he was saying that like the norm is 95, and I was like, well, wouldn't you want it higher? And then I was reading a study, and they had theirs higher, but that makes a lot more sense.
Cool. And so when we're we define our alpha nice and early before we run any tests. And then we're going to be comparing that alpha to the p-value, and that p-value, it's a single number, right? And if that p is low, we reject the null hypothesis, right? If that p is lower than the alpha, then we reject the null hypothesis. If the p is higher than alpha, we fail to reject the null hypothesis, right? I'll give you all some concrete examples of that when we get to the t-tests.
Hey, Ryan. So on
Stephen.
the significance level, like on your alpha, I read that, depending on where you set your alpha, can increase or decrease the chance of having a type 1 or a type 2 error.
Yep.
Pop up.
Yeah, if your alpha is higher, you might have more type 1 errors because we're comparing alphas and p-values. We're not going to, we select, the practitioners select the alpha. Our statistical tests give us back the p-value, and it really comes down to an if-else statement, right? If the p is less than alpha, then we reject the null hypothesis. Otherwise, we fail to reject the null hypothesis. And this is one of those pieces of like scientific epistemology, which is a mouthful to say, but like, how do we know what's real about the world? And we have pretty, we can't prove that the sun will come up tomorrow, but we can disprove that it won't come up tomorrow. Historically, in new test after new test, every day that we encounter, we disprove the hypothesis, we reject the null, right? But we can't just say the sun's going to come up tomorrow. It's a weird way of thinking. It's different, but it's all starting with that null hypothesis. So whatever the scenario is, just always our null hypothesis is that there is null difference or null effect or null relationship between things we're measuring. And so the alternative hypothesis is generally there is an effect, or there is more of an effect, right? Yes, absolutely. Absence of evidence is not the evidence of absence. Absolutely the case. Cool. I'm going to save these little notes so far, just so I don't lose them in case something comes up. So we'll say hypothesis. We'll put this in the statistics exercises. Why not? There we go. All right. Y'all ready to keep going? Let's keep on going. All right. You may see your alternative hypothesis noted with an H sub A or an H sub 1. I mean, the big deal is you always have two hypotheses, the null hypothesis and your alternative. So our general hypothesis testing workflow is we choose the right type of test for our data. So we're introducing three in the curriculum. We're introducing t-test, correlation, and then chi-squared. And it depends on what kind of data you have, categorical or continuous. We set our desired confidence level and our alpha, and that means setting our alpha before any testing, right? And then we form our hypotheses. So when we form the hypothesis, we form the null, which we need to write it out. Just even though it's accepted that the null hypothesis, that there's no difference, write it out, then write your alternative hypothesis. And then we'll calculate the step 3 here. Once we have everything set up, then we can actually crunch the numbers. We can run the appropriate t-test or the appropriate test statistic, whether if it's a chi-squared or t-test correlation, and we're going to get back a p-value. And the p-value is the probability we observe this result due to chance, or it's the same thing as saying the probability of seeing the result we get if the null is true. So right here, step 3, we're calling some statistical library code in Python. We're not doing a bunch of this stuff by hand. I don't want to live that way. And then the conclude based on the above statistics. Well, that's when we take a look at what we've got and we say, okay, given our alpha, given our p-value, given the null hypothesis, is the p less than the alpha? Do we reject the null or do we fail to reject the null? What kind of conclusions can we take? Okay. Let's see. Let's see, we've got central limit theorem, null and alternative, hypothesis test results, type 1 and type 2 error, which we talked about. I'm feeling crazy. Are y'all feeling crazy? Would y'all like to see an actual, rather than just doing no code this whole lesson, would y'all like to see some code? Okay, cool. I'm going to reach a little bit into the future because we were working with, I'm going to introduce a t-test in here somewhere. There we go. We get a happy little Jupyter notebook going. This is gonna it'll bleed a little bit into the t-test, but I think it'll help, right? So let's do Python notebook. And then for the imports, we will be making some new friends. What I'm going to do is start with NumPy and the Pi data set. So I have a little data set, and then we'll do test. Intro hypothesis test. Okay, so I'm going to make a little data frame here, and this will be, I don't know if y'all have seen the tips data frame before. I think y'all have. So I'm going to go into the details on the different, there's a couple of different types of t-tests, but for right now, I want to compare, let's see what we're doing here. With the t-test is, let's say we want to compare, this will be good with a binary. So I'll start with what we call a one-tailed t-test example. And our business question, let's always start with a business question, right? Our tips on Sunday hire were significantly different than the rest of the week. See how we have different times, we have different table sizes, we have whether or not the table smokes. And if we look at all of the folks on Sunday, all of our diners on Sunday, or our customers on Sunday, that is a subgroup of the entire population, right? So let's see if from the perspective of the business, we want to focus on the business. From the perspective of the employee, we might want to try to maximize tips, right? So the null hypothesis, we always state our null, is that there is no difference, which is a way of saying tips are the same on Sunday versus the entire week. Okay. Now the alternative hypothesis is that there is a difference between Sunday tips and the entire week. Okay, so this first setup here, where I didn't have any code, start with the business question and try to refine the business question into a way where we're comparing categorical or continuous variables. The null hypothesis is that there is no difference tips are the same on Sunday versus the rest of the week. So we're going to be comparing the means of the entire week and the means of just the Sunday tips. So step one, let's set our null hypothesis. Why not make it a string? So I can put this, so we'll say Sunday tips are the same as the rest of the week. Our alternative hypothesis, Sunday tips are different than the rest of the week's tips, right? Now, how rigorous do we want to be here? Our confidence level, we might want to say 0.95. So our alpha, 1 minus the confidence level. And this is all part of our setup here. This is all part of the setup. Haven't run any other code, right? Notice how I'm setting my alpha nice and early, so I'm not fudging the alpha later to like lasso in some of the results. It's kind of a big crisis in reproducible results, right? People goofing with their alpha levels. So here's what I'm going to do. I'm going to make a subgroup, since we'll talk about the different kinds of t-tests a little bit later, but we'll make a subgroup for Sunday. So let's do Sunday will be df, where the day is the string Sunday. We'll take a look at the Sunday data set. Oh, it's S-U-N, not the word Sunday. I'm glad I double checked. Okay. Y'all with me so far? So, but when we're looking at, let's compare, let's take a peek at the Sunday. And what's the thing we're interested in is the tip, right? Because we said so, Sunday tips and the rest of the week. So we can do Sunday dot tip dot hist, and we get a happy little histogram of the Sunday tips. And then, right, it's not too shabby. If we looked at the entire data frame, df.tip.hist, we have a different shape. There's some similarities and there are some differences, right? But we want to compare these two with some rigor rather than just eyeballing these two things, right? Let's see. So it's at this point in the game, I'm reaching ahead a little bit because we're in the overview, reaching into the t-test just a little bit. But what we'll do here is we'll set up the t-test. I think I imported stats. I don't think I imported stats. I have to import stats. Let me find my import. Handy dandy. Here we go. Here's our new friend. From SciPy, import stats. Okay. From SciPy, import stats. And here's what this is going to give us: the stats library. And here's what I can do with it. I will say stats.ttest. OneSamp is the name of the function. So if you are doing a one-tailed test, use the t-test OneSamp function. And we will compare the Sunday tip to the entire population. of tips. And then we'll send in the mean here. So check this out. We run this, we get a t statistic, which is why it's called a t-test. And then we get a p-value. And we will be comparing that p-value to alpha. Remember our alpha? Our alpha is 0.5. Don't worry about the rounding error. I didn't break math. Python didn't break math. It's just it's kind of like a never-ending fraction, but in binary. So don't worry about it. Our alpha is 0.5, right? So what we can do here is we can compare, literally compare, if p is less than alpha. And we can also print out p. Oh man, it's so close, right? It's so close, 0.7, 0.5. Why don't we fudge the numbers so we can get our foundation and get our paper printed? Like, this is why you set your alpha nice in first. So if p is less than alpha, we say we reject the null hypothesis. Otherwise, we fail to reject the null hypothesis. So here's the big one. Failing to reject the null does not equal accepting the null. So what we're seeing is that, and I love this, I love being able to bring an if else to the party, because then if we've already decided on our alpha, we can use our the appropriate hypothesis test to get our p-value. We compare our p-value to the alpha, and here's what's happening here. These are so close, right? But because we already made a commitment to this alpha of 0.05, I'm not going to fudge my numbers. I might explain that we're close to the threshold, though, right? But looking at this, we fail to reject the null hypothesis. So failing to reject the null is not the same thing as accepting the null, but we kind of move forward with the null. What we do here is really what we did here is we failed to I might put it as, there is a difference, right? If we compare these two histograms, because that's what the t-test is doing, really underneath the hood. There's some similarities, there's some differences, but we're not comfortable, because we're beneath our alpha here. We're not comfortable rejecting the null hypothesis and saying that they are different. So we move forward saying we didn't reject the null. Okay. Would y'all like to see another example of this, another setup here?
Hey Ryan,
Hey,
I have
Ryan,
a.
can I?
Oh, go ahead, David.
Oh, go ahead, Justin. No, you can go ahead. I'll go. Go ahead.
I was just wondering if you could highlight why we did the one-tailed test on this versus the two-tailed test. I guess I was thinking that it would be a one-tailed test if we were specifically saying tips are either greater than or less than. But here we just said, is there a difference? But it's still a one-tailed test.
Mm-hmm. That's a good question. Let me find your answer here. My answer is we're comparing a subgroup to the population in this case. So, tailed.
Oh, so the specificity isn't necessarily greater than or less than. It can be categorical, like Sunday versus.
Yeah.
Got it.
Yeah. So kind of merging into the next lesson a little bit, but if we're comparing two different subgroups, that would be a two-tailed rather than the one subgroup to the population. Does that help?
Yes, I think I was thinking that it was all dependent upon whether you wanted to see if there was any difference versus like a greater than or less than difference, but that was incorrect. Thank you.
Hey, Ryan, my question just on confidence levels. You know, you go like 90, 95% or 97 or 99.5. Is it when trying to establish that beforehand, is there almost like a, based on the industry that you're in or whatever you're trying to test, like a, I don't want to call it like a standardized alpha that you're using, but what can you look at besides past papers that you have done something
with that confidence level and being able to set our alpha? I'd say go with established paradigms for that industry, right? Or what's been done before. If somebody is a flim flam artist, they're going to set their confidence level to 50%, right? If they're an outright liar, they'll set their confidence level to 1, or their alpha to 1, right? Accept anything. Generally, the highest alpha that I see generally is 0.05, and that's usually in like economic studies, or usually some business studies are pretty okay with a 0.05 alpha. I wouldn't want to use an alpha of 0.05 if I was working with nuclear physics, right? Or electronics manufacturing, or working with semiconductor manufacturing, or measuring tolerances there, right? In fact, here's a fun one. The t-test actually comes to us from, I don't remember the gentleman's name because he used a pseudonym called Student. He wrote a paper called introducing the idea of a t-test, called himself Student, but his actual day job was comparing groups of different kinds of beer at the Guinness Brewery. So the individual who came up with the t-test math and the statistics there worked for Guinness Beer, of all places, in beautiful Ireland, right? And was comparing different, basically using the t-test as an internal tool, and didn't want to give away, I mean, this individual developed it, didn't want to get in trouble with their employer, so they published a paper called it Student. So if you see Student t-test, it's not because you learn the t-test in school and you are a student, it's because that was the pseudonym, the writing name of, I forget the cat's name who came up with the t-test and wanted to publish without Guinness being on his back about it. So it's comparing different barrels of beer and quality. Actually, like, imagine the things that we could compare here. We could compare beer that's been on the shelf 3 months versus beer that's been on the shelf 3 days, right? We can measure some measurable inside of that and compare the subgroup to the population, or compare different groups among each other.
So increasing sample size, does that allow us to have would that decrease our confidence level that we have to have, or increase?
Increasing your number of samples is a good thing. It's definitely a good thing to increase, right, to crank up your number of samples. One of the biggest challenges to hypothesis testing and machine learning is not having enough data, or having data that's not representative of what we're measuring, right? So more data is good. We don't want to do a t-test, correlation, or chi-squared with like 20 observations or 10, right? In one of my business stats classes ages ago, the magic number was 24, but I could personally, at this point in my career, I consider that hogwash. I want hundreds, I want thousands of observations if I can get them. let's see. Faith is hopping in to help. This is excellent. You were asking about one-tailed versus two-tailed test. I was talking about one sample. So I was talking about one sample and two sample tests, but using incorrect vocabulary. My apologies. So let me fix myself. Let me spell check myself before I spell wreck y'all. One sample t-test. There we go. Forgive me, please. So looking at the overview, in the overview, we're introducing this concept of the central limit theorem. This is a little bit of a divergence. If these tools that we have here, the t-test, correlation, and at least t-test and correlation are predicated on having a normal distribution. And if you don't have a normal distribution, here's something you can do. You can sample from that non-normal distribution, and your sampling distribution will be more normally distributed. It's this crazy wild property. It's driven people nuts trying to prove or disprove the central limit theorem. We're not going to need this here so much because the rest of the course will have more sophisticated tools than just t-tests and correlation tests. But it bears mentioning, if you ever see the central limit theorem, what this is saying is if you sample from a non-normal distribution, you will get a normal distribution in your sampling distribution. Yeah, and Justin, thank you for your question. My apologies for being off a little bit there. I need to update my notes here. So let's see. Update till or sample. All right. So our null hypothesis is always and forever that there's some sort of status quo. There's no change, no difference, no relationship, right? No correlation, no similarity. And once we have our hypothesis test results, we care about that p-value. And folks, we're comparing that p-value to our alpha. If the p is lower than the alpha, we reject our null hypothesis. If it's not, we're not losing anything, but we can't say clearly that we accept the null hypothesis, and we certainly can't accept the alternative hypothesis. So even if we have a distribution like this, these two, the Sunday tips versus the rest of the entire week's worth of tips, there's not a significant difference here. This is why we fail to reject the null hypothesis. Okay, let's see. We've talked about our error rates. Okay, this is good. I'm going to get us back to our our coffee example here, right? If we make a claim that Coda DS students drink more coffee than web dev students, that would be our alternative hypothesis. Our null hypothesis is that they are the same, right? And whether if we're talking about correlation, t-tests, or chi-squared, the name of the game is the null hypothesis is that there's null difference, null relationship, right? That's the biggest thing to take away here. Okay, let me see. We have some exercises that are not code oriented. And these first couple of exercises here will get you into this practice and this habit of take the problem, turn that business statement or that business question into an answerable statistical question, form your null hypothesis, and then form your alternative hypothesis. I don't think these exercises are going to take us very long at all, but we're coming on the top of the hour, so it's about good time for a break anyway. Has the network latency gone up since we switched internet providers? Is the website redesign any good? Like usually questions we get aren't formed in a way that can be immediately answered statistically. So we'd have to find out, what do we want to measure? What are our measures of a website being good or not, right? And then we can compare those two measures. So this will take a little bit of creativity as well. Is our television ad driving more sales? I think that's a little bit easier. And you will set these up as some text in a new Jupyter notebook called hypothesis testing. And then we'll spend a little time on these exercises. We'll take a break, and then we'll proceed forward with the t-test. A little bit more on the t-test, rather.